Okay, let's unpack this. Imagine you're navigating the world of software quality, aiming for that solid understanding that's globally recognized. Maybe you're prepping for a meeting, diving into a new role, or just, intensely curious.
hmm
One name keeps coming up, ISTQB. They published the syllabus, and we're zeroing in on the very latest, the foundation-level syllabus v4.0.1 from September 15th, 2024.
That's the one.
Forget wading through dense documents. Think of this deep dive as your expert-guided shortcut to the absolute core of what this foundational material covers. We're going to cut through the jargon, explore the fundamental concepts, uncover surprising insights, and maybe even figure out what testing really is.
Yeah, and why it matters maybe more than people think.
Exactly. And how this syllabus helps advance the entire profession. Our mission, to help you quickly grasp the most important nuggets from this essential document.
That's exactly right. And this syllabus isn't just some dry document for exam candidates. I mean, while it does serve as the official basis for the foundation level certification, its purpose kind of ripples out into the entire software world.
Right. So who else benefits, beyond someone just studying for the test?
Well, think about the member boards. They translate it, they accredit training providers. It ensures consistency worldwide.
Okay.
Then you've got certification bodies using it to develop the actual exam questions, so they're directly tied to what you need to know. Training providers, they build their courseware around it.
Naturally.
And for the broader software community, it acts as a kind of shared language, a foundation for books, articles, and really advancing the profession itself. It gives everyone that common baseline understanding.
It really is foundational then. And the syllabus, it doesn't just list topics, it outlines what a certified tester should actually be able to do, what they call business outcomes. What are some of those practical abilities?
Yeah, they list quite a few, I think 14 in total, but you can see the clear focus on real-world application. A certified tester should understand testing's benefits and concepts, know how to align testing with the development lifecycle, manage activities like planning and reporting.
Okay, the practical stuff.
Crucially, they should be able to write clear defect reports, understand risks, leverage test automation appropriately, and work effectively within cross-functional teams. It's about being a valuable contributor to quality, not just someone who, follows a script.
Okay, that makes the why get certified much clearer. It's about practical competence. Let's jump into those core concepts then. At its heart, what is software testing, according to this syllabus?
Right. It defines software testing as a set of activities aimed at two main things: discovering defects and evaluating the quality of software work products. The things we actually test, we call them test objects.
And this is where that common misconception comes in, isn't it? People often think testing is just, clicking buttons and seeing if it crashes.
Precisely. The syllabus is very clear. Testing is far more than just executing tests. It's a whole process that includes planning before writing any test cases, analyzing requirements, designing the tests, implementing them, executing, and then completion activities once testing is done.
Right.
And all of this must be aligned with whatever software development lifecycle the team is using. That's key.
Aligning with the SDLC. Got it. Now, there are two terms that get mixed up all the time: verification and validation. How does the syllabus distinguish them?
Okay, think of it this way. Verification is checking if you built the product right.
Right.
Are we meeting the specifications and requirements? Validation, on the other hand, is checking if you built the right product. Does it actually meet the users' and stakeholders' needs in its intended environment?
Ah, okay.
So testing encompasses both making sure the system does what it's supposed to do and that what it's supposed to do is actually useful and correct for the business.
That right product versus product right distinction is key. So with those definitions in mind, what are the typical objectives or goals when you're testing something?
Well, the goals can shift depending on the project or context, naturally. But generally, you're evaluating work products like requirements or the quality of the code. You're deliberately trying to cause failures to find defects.
You're trying to break it, basically.
In a controlled way, yes. You're trying to ensure you've covered specific parts of the system. It's about reducing the risk of poor quality, verifying requirements are met, and crucially, providing stakeholders with information so they can make informed decisions.
And building confidence.
Yes, building confidence that the software will work and ultimately validating its completeness.
So why is all of this even necessary? I mean, why do we need testing?
Well, software quality doesn't just happen, right? Testing is a critical form of quality control. It helps teams achieve their project objectives within those pesky constraints we always face: scope, time, quality, budget.
Always.
It's the primary way we identify defects before users do, which is pretty important. And let's not forget, in many industries, testing is legally, contractually, or regulatorily required. Compliance is a big driver.
Okay, another classic confusion. Testing versus quality assurance, or QA. The syllabus tackles this head-on.
Absolutely, and it's an important distinction. Testing is primarily product-oriented. It's a corrective activity focused on finding defects and evaluating the quality of the software itself.
Okay.
QA, on the other hand, is process-oriented. It's a preventive activity focused on improving and implementing processes across the entire development lifecycle, not just testing. QA is really everyone's responsibility, aiming to prevent defects from being introduced in the first place,
Okay.
based on the principle that, a good process leads to a good product.
So testing finds problems in the product, while QA tries to stop problems from getting into the process that builds the product. That makes sense.
Exactly. And test results are used by both. Testers use them to get defects fixed. QA uses them as feedback to see how well the processes are working and where they might need improvement.
Okay, perfect. Now, let's trace the source of those problems.
Right.
The syllabus defines the chain: errors, defects, failures, and root causes. Can you walk us through that relationship?
Sure. It typically starts with a human error, a mistake made by someone, say, a developer rewriting code, or maybe a business analyst writing a requirement.
Okay.
This error can introduce a defect into a work product, like a bug in the code or an ambiguity in a requirement. A defect is basically a static flaw sitting there.
Right, it's just waiting.
Exactly.
Yeah.
Now, if that defect gets activated, for example, if the flawed code is executed or the ambiguous requirement leads to a wrong implementation, it may lead to a failure.
May lead to one. Not always.
Not always. Conditions have to be right. But a failure is the visible, incorrect behavior, the system doing something it shouldn't or not doing what it should.
So error leads to defect. Defect potentially leads to failure. Got it. And failures can also be caused by things outside the software, like a network issue, right?
Yes, absolutely. Failures aren't always due to defects in the code itself. They can definitely be caused by environmental problems. And when a failure or defect is found, teams often perform root cause analysis.
To find the real reason.
Precisely, to figure out the fundamental reason it occurred. The goal is to fix the source of the problem, not just the symptom, to prevent similar issues cropping up again in the future.
It's like treating the illness, not just the fever. This breakdown is really helpful. Speaking of fundamentals, the syllabus lays out 7 guiding principles of testing these kind of timeless ideas that apply pretty much everywhere.
Yes, these principles are crucial for shaping your testing mindset. The first one, dating back quite a way, is key. Testing shows the presence, not the absence of defects. Meaning you can prove defects are there when you find them, but you can never test enough to definitively prove there are no remaining defects hidden somewhere.
Which leads directly into the second principle. Exhaustive testing is impossible.
Right. Unless your system is incredibly simple, you just can't test every single input combination, every single path through the code, every possible scenario. It's just not feasible. So you have to focus your efforts smartly, using techniques, prioritization, and risk assessment.
Makes sense. Principle 3 is a classic. Early testing saves time and money.
Absolutely. The earlier in the development lifecycle you find and fix a defect, whether that's through static reviews of requirements or early dynamic execution of code, the exponentially cheaper it is to resolve.
Yeah, I've heard that.
Catching a requirements error in a review might take minutes. Fixing that same misunderstanding after it's been coded, integrated, and tested can take days or even weeks.
Ouch. Okay, principle 4. Defects like to hang out together.
Yes, the defect clustering effect. It's like the Pareto principle. You often find that roughly 80% of the problems are concentrated in about 20% of the modules or features. This is vital information for risk-based testing. You target your efforts where the defects are most likely hiding.
And your tests themselves can get stale. Principle 5.
Right, tests wear out. If you keep running the exact same set of tests over and over, eventually they'll stop finding new defects in the parts they cover. You need to review, modify, and add new tests to challenge the system in different ways.
Unless it's regression testing.
Exactly, unless it's automated regression testing, where the goal is repeatable checking to ensure changes haven't broken existing functionality.
Okay. Principle 6 emphasizes context.
Yes, testing is context dependent. How you test a safety-critical system for, say, an airplane is fundamentally different from how you test a simple marketing website or a mobile game. There's no single right way to test everything. Your approach has to fit the situation.
And finally, the absence of defects fallacy. What's that?
This is crucial. Just because you've found and fixed all the known defects and verified that the system meets its written requirements, that's verification, that doesn't guarantee success.
What?
Because if the requirements themselves were wrong, or if the system doesn't actually meet the user's real needs or the business goals, it will still fail in practice. Verification isn't enough. You need validation ensuring it's the right product.
Those 7 principles really provide a solid mental model for approaching testing effectively. Okay, let's get practical. What does the typical testing process look like? What are the activities involved?
The syllabus describes a set of common test activities. Planning is first, then monitoring and control throughout, then analysis, design, implementation, execution, and finally, completion activities.
Is it always step-by-step like that?
No, not at all. It's important to realize these aren't always strict sequential steps. They can be iterative, they can overlap, and you absolutely tailor the process to your specific project and context.
Tailoring based on what factors?
Oh, lots of things. Who the stakeholders are, the team's experience level, the specific work products you're testing, the tools you have available, the chosen development lifecycle. All these influence how you structure and execute the test process. It impacts your strategy, the techniques you use, how much you automate, how you report, everything.
The outputs of all these activities are collectively called testware. That term covers a lot, doesn't it?
It really does. It's basically everything you produce during testing. Think test plans, test conditions you identify, the actual test cases, test scripts for automation, test data you prepare, set up instructions for test environments, the defect reports you write, progress reports, completion summaries, even lessons learned documents.
Wow.
And maintaining the integrity of all this testware through configuration management is vital, especially in agile environments where things change frequently.
Configuration management for testware.
Yeah.
Why is that so important? I mean, if you lose your code, you're obviously sunk.
Yeah.
But if you lose your test cases...
It's critical. Imagine this. If your test cases aren't versioned and managed properly, you might not be able to reproduce a test result later. You might not know which tests were run against which specific version of the software.
See.
Or you might run regression tests that are outdated because someone changed them without tracking. How can you trust your results? CM provides that necessary control, history, and traceability.
That makes total sense. And related to managing all this testware is the concept of traceability.
Yes, traceability is essentially linking related work products together. For testing, this is huge, linking requirements to the test cases designed to verify them, linking test cases to their execution results, and linking those results back to defects and maybe back to the original requirements again.
Why go through the effort of setting all that up? Seems like work.
It is work, but it's invaluable. Traceability helps you evaluate test coverage. Have we actually tested everything required? It supports impact analysis. If a requirement changes, which tests do we need to update or rerun? It aids audits, improves communication by clearly showing what's been tested against what standard, helps assess quality and progress objectively, and provides critical information for things like risk assessment and defect analysis. Without it, you're often just guessing about the completeness and impact of your testing.
It sounds like the paper trail that proves your testing is thorough and targeted. Now let's talk about the people. What roles are typically involved and what skills are needed?
The syllabus broadly describes 2 main roles. There's the test management role, which is about the overall planning, monitoring, and control of the test process, and the team.
The leadership aspect.
Right. And then there's the testing role, which is focused more on the technical engineering tasks like analysis, design, implementation, and execution of tests.
Can one person wear both hats? Or is it usually separate people?
Oh, absolutely. One person can wear both hats. In smaller teams, or even in certain agile contexts where roles are more fluid, one person might easily perform both management and technical tasks. The structure can be very flexible depending on the team and project.
And for the people in these roles, what skills go beyond just, technical ability or knowing the tools?
Good question. The syllabus highlights skills like thoroughness, curiosity, which is essential for finding those tricky hidden bugs, and carefulness. Communication and teamwork are absolutely vital.
Because you're always interacting.
Constantly, with developers, business analysts, users, managers. everyone, analytical and critical thinking are needed to design effective tests, while creativity helps you think of scenarios others might miss. And of course, technical knowledge helps with tools and environments, and domain knowledge helps you understand the business context and speak the same language as stakeholders.
You mentioned communication is key, especially when reporting defects.
Yeah.
That can be tricky, right? How do you do that constructively?
It's crucial because, let's face it, delivering bad news about defects can sometimes feel like a personal attack, even if it's not intended that way. And confirmation bias can make people resistant to findings that challenge their work. You need to communicate defect information objectively, factually, and constructively. Focus on the impact to the product and the users, not on blaming individuals. Frame testing as a collaborative effort to help the team build better software rather than just pointing out flaws.
That framing is important. The syllabus also touches on different team approaches, like the whole team approach. What's that about?
Yes, that often comes up in agile contexts. The core idea is that quality is everyone's responsibility, not just the testers. Testers work embedded in a cross-functional team alongside developers and business representatives.
So less siloed.
Much less siloed. The idea is anyone with the right skills can potentially pick up any task. Co-location or good virtual collaboration tools aids communication. Testers collaborate closely with business reps on acceptance criteria and with developers on test automation strategies, for example.
But sometimes you need a fresh pair of eyes, right? Yeah. Someone who isn't involved in the day-to-day development, that's test independence.
Exactly. The syllabus discusses the pros and cons of different levels of test independence. Benefits include having an unbiased perspective that might find different types of defects, and providing a more objective evaluation of quality.
What are the downsides?
Well, drawbacks can include the testers becoming isolated from the development team, potential communication issues, maybe even adversarial relationships if it's not managed well. There's also a risk developers might feel less responsible for quality if testing is seen as purely an external gatekeeper function, or testing becomes a bottleneck.
So it's a balance.
It really is. The right level of independence depends heavily on the context for safety-critical systems, for instance. A higher degree of independence is often required or even mandated.
Makes sense. Let's shift to how testing fits into the bigger picture of the software development lifecycle, the SDLC. Does the SDLC model you choose really dictate how you test?
No, absolutely. The SDLC model, whether it's sequential like waterfall or iterative, incremental, or fully agile, profoundly impacts how you plan, execute, and manage your testing activities. Well, it affects the timing of activities, for one. It influences the level of detail needed in documentation. It shapes the techniques you might favor, the extent and type of automation you implement, and even the specific roles and responsibilities within the team.
Can you give an example of the difference, like sequential versus agile?
Sure. In a strict sequential model, a lot of the dynamic testing might happen quite late in the project because you need the fully compiled and integrated code. So static testing and detailed test design based on specs would be the focus earlier on.
Okay.
In iterative or agile models, you're delivering small working increments frequently. This means you need to perform static and dynamic testing at all levels, component, integration, system within each iteration. Fast feedback is absolutely critical.
Which implies more automation.
Exactly. Heavy test automation, especially for regression testing, becomes essential. Agile also often favors lighter documentation and might lean more towards experience-based testing techniques alongside the structured ones, just because the cycles are so much faster.
Despite those differences, are there universal good testing practices that apply across any SDLC?
Yes, definitely. Some core principles hold true regardless of the model. Ideally, for every development activity, there should be a corresponding testing activity planned.
Like pairing them up.
Right. Each test-level component, system, acceptance should have clear, distinct objectives. And critically, starting test analysis and design as early as possible in the relevant development phase is always beneficial. Getting testers involved in reviewing requirements or user stories while they're still drafts, for instance, this really supports that idea of shift left.
Ah, shift left. That's a popular term. What does it truly mean according to the syllabus? It's not just doing everything at the beginning, is it?
No, not exactly. Shift left is really about applying that third testing principle. Early testing saves time and money more broadly and proactively. It means moving testing activities or activities that benefit testing like reviews and static analysis earlier in the life cycle.
So finding issues sooner.
Precisely. It doesn't mean you neglect later testing stages, but you front-load efforts where possible. Examples include reviewing specifications and code early and often, writing tests before or concurrently with the code being written, using static analysis tools as part of the build process, and integrating testing into continuous integration, continuous delivery pipelines.
Does shifting left always mean more work up front?
It might mean more effort or cost earlier on, perhaps in setting up processes, training people, or implementing tools. But the huge potential payoff is finding and fixing defects when they are cheapest and easiest to resolve, potentially preventing major rework, delays, and costs later down the line. It's really an investment in preventing problems.
The syllabus also talks about test-first approaches like TDD, ATDD, and BDD. How do they embody shifting left?
These approaches are prime examples because, by definition, the tests are written before the code they're intended to test. They actively drive the development process.
Okay, can you briefly explain each TDD?
TDD, test-driven development, typically involves developers writing automated unit tests before writing the production code to make those tests pass. It guides the coding at a very low level.
ATD.
ATDD, acceptance test-driven development, focuses on the system's external behavior. Tests are derived from acceptance criteria, often collaboratively with business stakeholders, before the feature is coded. These tests define done for a feature.
And BDD.
BDD, behavior-driven development, is similar to ATDD, but emphasizes describing the desired behavior in a structured natural language format, often using given-when-then scenarios. These scenarios are discussed collaboratively and can then be turned into executable tests, again, often before or during coding.
So these tests stick around?
Yes. In all these approaches, the tests typically persist as automated tests, forming a valuable regression safety net and living documentation of how the system is supposed to behave.
Makes sense.
Yeah.
And how does the major trend of DevOps fit into this picture of testing and the SDLC?
DevOps is fundamentally a cultural and organizational shift. It focuses on breaking down silos between development, dev, and IT operations to enable faster, more reliable software releases through collaboration, automation, and tight feedback loops.
And for testing, how does it impact testing?
For testing, this is huge. Continuous integration and continuous delivery, CI/CD pipelines, are inherent to DevOps, and these pipelines heavily rely on automated tests at multiple levels to provide that fast feedback.
So it promotes automation.
Massively. It naturally promotes shifting left static analysis tools, and component tests can be run automatically with every code commit. DevOps practices also often provide more stable, automated test environments and increase visibility into non-functional aspects like performance early on. Automation reduces manual drudgery, and the automated pipeline minimizes regression risk during frequent releases.
What are the testing challenges in a DevOps world, though? It can't be all easy.
Definitely not. Setting up and, crucially, maintaining that robust automated pipeline requires significant effort, the right tools, and specific skills. It's a big investment.
Right.
And while automation is critical, you still absolutely need manual testing, especially things like usability testing and exploratory testing from a true user perspective. Fitting that effectively into very fast delivery cycles can be a challenge.
Okay. Finally, under the SDLC umbrella, the syllabus mentions retrospectives. What's their role?
Retrospectives are a core feedback mechanism for process improvement, typically held at the end of an iteration, a release, or a project phase. The team gets together to reflect objectively on what went well, what didn't go so well, and identifies specific actionable steps to improve their process going forward.
So learning from experience.
Exactly. Those improvement actions, often recorded in completion reports, are vital for continuous improvement in testing effectiveness and efficiency. It's about embedding learning into the way the team works.
Learning from experience to continuously get better. That's a great principle itself. Okay, let's talk about the different types and levels of testing. These terms sometimes get confused. How does the syllabus organize these?
Yeah, they can be confusing. The syllabus makes a helpful distinction between test levels and test types. Test levels are generally related to the structure of the system being developed and map onto SDLC activities, testing individual components first, then how they integrate, then the whole system, and so on. Levels can sometimes overlap in practice.
Okay, levels relate to structure and SDLC phases. What about test types?
Test types relate more to specific objectives or quality characteristics you're trying to evaluate. Think functional testing, performance testing, security testing, usability testing. The key difference is that a specific test type can potentially be performed at multiple test levels. For example, you could do performance testing at the component level and also at the system level.
Got it. So what are the main test levels described?
The syllabus typically discusses 5 common ones. First is component testing, often called unit testing. This is testing individual software components or modules in isolation, often done by developers using stub code or drivers.
Then integration.
Right. Component integration testing focuses on testing the interfaces and interactions between those components after they've been integrated. Then comes system testing, where you test the complete integrated system as a whole, looking at both its functional and non-functional behavior against the overall requirements.
And integration with other systems.
Yes, that's system integration testing. This focuses on testing the interfaces and interactions between the system under test and other external systems, services, or infrastructure it needs to work with.
And the final level.
Acceptance testing. This is usually the most formal level, focused on validation, determining if the system meets the needs of the users and the business and is ready for deployment. This category includes several kinds, like user acceptance testing, UAT, often done by end users, operational acceptance testing, OAT, by system admins, contractual or regulatory acceptance testing, and also alpha testing, internal, and beta testing, external user feedback.
Okay, 5 levels. Now, what about test types? What are the big categories there?
The 2 main umbrella categories are functional testing and non-functional testing. Functional testing is all about what the system does, testing its functions against specified requirements or behaviors. Does it perform the calculations correctly? Does it store the data properly? Does it produce the right output?
And non-functional testing.
This is about how well the system does what it does, evaluating its operational quality characteristics.
That sounds broad. What are some examples of non-functional characteristics, maybe based on standards like ISO 24010?
Exactly. Standards like that provide a good framework. Think about performance efficiency speed, response time under load, stress handling. Compatibility doesn't work correctly across different browsers, operating systems, devices. Usability, is it easy to learn, easy to use, accessible?
Okay.
Then there's reliability. How stable is it? Does it handle faults gracefully? Can it recover? Security protection against threats, vulnerabilities. Maintainability, how easy is it to modify or fix? Portability, how easily can it be moved to another environment? And in some contexts, safety testing is critical.
And can you do non-functional testing early?
Yes, definitely. The syllabus points out that non-functional testing often requires specific tools or environments, but aspects of it, like performance modeling or security reviews of the design, can and should start early in the life cycle.
Makes sense. There are also specific types of testing you do specifically after changes or fixes have been made, right?
Yes, confirmation testing and regression testing. They often go together. Confirmation testing, sometimes just called retesting, is simple. You rerun a test case that previously failed after a defect has supposedly been fixed, just to confirm that the fix actually worked.
And regression testing.
Regression testing is broader. After a change or a fix has been made, you need to check that this change hasn't introduced new defects or broken anything else in parts of the system that were previously working fine. It's about checking for unintended side effects.
Do you just rerun all your tests?
Not necessarily, and often not feasibly. You definitely need to perform some impact analysis before doing regression testing to figure out which areas of the system might realistically have been affected by the change and focus your regression tests there.
Regression testing sounds like a perfect candidate for automation, especially if you have lots of tests.
It absolutely is. It's probably the most common and beneficial use case for test automation, especially with CI/CD pipelines where you need that fast feedback loop after every change. Automated regression suites provide that safety net. And both confirmation and regression testing are needed at pretty much any test level where defects are fixed or changes are made.
And one more type, maintenance testing. What's that?
This happens on a system that's already deployed and operational. It's in maintenance. It's testing changes made to that live system, things like enhancements, corrective bug fixes, or maybe configuration changes. It also covers testing the environment when the system is migrated to new hardware or upgraded, for instance.
Does it also cover shutting a system down?
Yes, it can also include testing related to retiring a system, like ensuring data is correctly archived and can be restored if needed later. The scope of maintenance testing depends heavily on the risk associated with the change and the size and complexity of the system being changed.
Okay, that covers dynamic testing at different levels and for different purposes pretty well. But we said earlier, testing isn't just execution. There's a whole chapter in the syllabus dedicated to static testing.
Right, and it's incredibly important. Static testing is essentially evaluating work products without actually running the software. It's done either manually through various types of reviews like inspections, walkthroughs, or informal reviews, or sometimes with the help of tools like static analysis tools that examine source code or models.
It's the opposite of dynamic testing, which requires execution.
Exactly.
Why bother testing without running the code? What's the real value?
This is where that early testing principle really shines. Static testing allows you to find defects earliest in the life cycle, often in requirements or design documents, long before any code is even written. Dynamic testing simply can't reach those stages.
Okay, so finding things earlier.
Yes, and it can find defects that are hard or sometimes impossible to spot dynamically, things like unreachable dead code, deviations from coding standards, maintainability issues, or security vulnerabilities in the code structure itself. Plus, it helps build confidence in the quality of the work product being reviewed, verifies requirements against actual business needs before coding starts, creates shared understanding among the team members, and generally improves communication.
And it's cheaper.
Often, yes. It's generally much cheaper and easier to fix defects found statically in documents or early code compared to fixing them after they're deeply integrated into a running system.
What kinds of defects are static techniques particularly good at catching?
They're great for finding requirements issues like ambiguity, inconsistency, or missing requirements. Design flaws. Certain types of coding errors, like using undefined variables, potential infinite loops, or specific security vulnerabilities, like potential SQL injection points if you know what patterns to look for. Also, deviations from coding standards, interface mismatches between different modules, and even gaps in planned test coverage items identified before you even write the detailed test cases.
What work products can you actually examine statically? Is it just code and requirements?
Oh no, almost anything readable that has some kind of structure can be reviewed. Requirement specifications, user stories, acceptance criteria, design documents, architecture diagrams, source code obviously, test plans, test cases, even user manuals, models, project plans, or contracts. Static analysis tools generally work best on formally structured artifacts like source code or specific types of models.
Can you review anything, like third-party software?
Generally, you can't static test third-party executables because you don't have the source code and there might be legal restrictions. But you can review the documentation or contracts related to them.
Got it. The syllabus describes a general review process based on standards. What are the key steps in that process?
Right. It outlines a structured framework that's adaptable to the context. It typically starts with review initiation. That's the planning phase, defining the scope, objectives, assigning roles, preparing the materials, and the participants.
Okay, preparation.
Then comes the individual review, sometimes called pre-work or individual preparation. Each reviewer examines the work product independently, identifies potential anomalies, makes recommendations, or notes down questions.
Then they discuss.
Exactly. Next is communication and analysis. This is often where a review meeting happens, but it can be done electronically too. The team discusses the findings, analyzes the anomalies, decides on their status, is it really a defect, assigns ownership for actions, and agrees on the next steps or overall quality level.
And finally,
fixing and reporting. The author or responsible person fixes the confirmed defects. The work product might be re-reviewed or formally accepted based on predefined exit criteria. And importantly, the results of the review metrics, defects found, lessons learned, are reported.
And who typically participates in these reviews? What roles are involved?
Several key roles are usually identified. There's the author, who created the work product being reviewed, the moderator, who facilitates the review meeting, ensures the process is followed, and mediates discussions. Reviewers, who actually perform the examination. The scribe, who records the identified anomalies, decisions, and minutes during the meeting. Often there's a manager involved who decides what gets reviewed and allocates resources. And sometimes a dedicated review leader who has overall responsibility for the review process itself.
Can roles be combined?
Oh yes, in practice, especially in smaller teams or less formal reviews, roles are often combined. The moderator might also be the scribe, for example.
And there are different types of reviews, varying in how formal they are.
Yes, the syllabus usually distinguishes between a few main types based on formality and objectives. Informal reviews are often ad hoc, maybe just two colleagues looking over something. There's no strict process or formal output. The main goal is just anomaly detection.
Okay, casual.
Then there are walkthroughs. These are often led by the author of the work product. They can have multiple objectives, evaluating quality, educating team members about the content, gaining consensus, and also finding anomalies.
And the most formal.
That's typically the inspection. Inspections are the most formal type, following a complete, defined process with specific entry and exit criteria. The main objective is maximum anomaly finding. Metrics are usually collected and analyzed, and crucially, in a formal inspection, the author cannot act as the review leader, moderator, or scribe to maintain objectivity.
How do you choose which type to use?
You choose based on the objectives you have for the review, the criticality of the work product, the project context, available time and resources, regulatory requirements, and even the team's culture.
What makes a review successful? Beyond just having the right people in a room or following the steps.
Good question. Several factors contribute. Having clear, agreed-upon objectives and exit criteria before starting is crucial, and making sure the objective is not to evaluate the author personally.
Right.
Using the appropriate review type for the goal, reviewing manageable chunks of information, not huge documents all at once, providing timely and constructive feedback, giving reviewers adequate preparation time, having management support for the review process, making reviews a positive part of the team culture, not a chore, providing training for reviewers, especially for formal techniques like inspections, and having well-facilitated meetings, especially for the more formal review types.
You mentioned earlier the value of early stakeholder feedback, often facilitated through reviews. Can you just reiterate those key benefits again?
Sure. Reviews are a fantastic mechanism for getting that early feedback. They facilitate early communication of potential quality problems, especially misunderstandings and requirements, before they get built. They help ensure changes are understood correctly by everyone. They improve the whole team's understanding of what they're actually building. They help the team focus on delivering genuinely valuable features. And overall, they positively impact risks by catching problems when they're small and easy to fix, preventing them from propagating through the system. It's really a proactive way to improve both quality and communication.
Static testing sounds like a really powerful prevention technique then. Okay, now let's dive into the core of test execution prep. Test analysis and design techniques. These are the systematic ways to actually create test cases, right?
Exactly. Test techniques help you systematically go from the test basis, which could be requirements, user stories, code, design specs, whatever, to specific test conditions you want to cover, and then to concrete test cases, including identifying the necessary test data.
Why use techniques? Can't you just wing it?
You could, but techniques help you create a relatively small but sufficient set of tests from what is often a virtually infinite number of possibilities. They provide a structured, repeatable way to achieve a defined level of coverage and increase the chances of finding important defects efficiently.
Makes sense. The syllabus classifies these techniques into 3 broad categories.
Yes, black box techniques, white box techniques, and experience-based techniques.
Okay, let's break those down. Black box first. What does that mean?
Black box techniques, also called specification-based techniques, are used when you derive your tests solely from the specified requirements or behavior of the system without looking at its internal structure or code. The test cases are independent of how the software is actually implemented.
And what are the most common black box techniques mentioned in the syllabus?
The big 4 usually covered are equivalence partitioning, EP, boundary value analysis, BVA, decision table testing, and state transition testing.
Okay, let's start with equivalence partitioning, EP.
Right. EP involves dividing possible input data, output data, or other relevant data into partitions or groups where you assume all values within a single partition will be processed identically by the software.
So you only need to test one value from each group.
That's the idea. You test one representative value from each partition, assuming it covers all the others in that group. This includes identifying partitions for valid data and partitions for invalid data. For coverage, you aim to exercise at least one value from every identified partition.
What if you have multiple inputs?
If you have multiple sets of partitions, for example, for different input fields, a common coverage goal is each choice coverage, which means picking one value from each set in your test cases, yet not necessarily testing all possible combinations of values from different partitions.
Okay. Next, boundary value analysis, BVA.
BVA builds directly on EP. It's based on the empirical observation that errors often occur right at the boundaries or edges of those equivalence partitions.
So you focus your tests there.
Exactly. Instead of just picking any value inside a partition, BVA specifically tests the values right on the boundary and just off the boundary on either side. The syllabus often mentions 2-value BVA, testing the boundary value itself and the first value just off it, and 3-value BVA, testing the value just before the boundary value itself, and the value just after it. 3-value is generally more rigorous.
Give me an example.
Sure. If an input field accepts integers from 1 to 100, the boundaries are 1 and 100. 3-value BVA might test 0, 1, 2, and 99, 100, 101.
Got it. Decision table testing. When would you use that?
This technique is excellent for testing requirements that involve complex combinations of conditions that lead to different actions or outcomes. Think complex business rules like determining an insurance premium or a shipping cost based on multiple factors.
How does it work?
You create a table listing all the relevant input conditions and the resulting actions or outcomes. Then you systematically identify the minimum set of rules, columns in the table, that cover all the unique and relevant logical combinations of those conditions. It's a great way to ensure you haven't missed any important scenarios in complex logic.
And the last black box one. State transition testing.
This technique is designed for systems or components that exhibit different behavior depending on their current state, and the events or inputs that trigger transitions between states.
Like what?
Think of a user login sequence: logged out, entering credentials, logged in, logged out, an order processing workflow, new page shipped, delivered, closed, or even the different states of a traffic light.
How do you test it?
You model the states and transitions, often using a state diagram, and then design tests to achieve specific coverage goals. Common goals include visiting every state, exercising every valid transition between states, which is most common, or sometimes for more rigor, especially in safety-critical systems, trying to trigger invalid transitions as well.
Those are powerful ways to derive tests systematically, just from specifications. What about white box techniques, where you do look at the code?
Right. White box techniques, also called structure-based techniques, use knowledge of the internal structure, design, or code of the software to derive test cases. The syllabus typically highlights two fundamental ones: statement testing and branch testing.
Statement testing aims to
Execute every executable statement in the code at least once during testing. Coverage is measured simply as the percentage of statements that were executed by your test suite.
and branch testing. Is that different?
Yes, branch testing is generally considered stronger. It aims to execute every possible outcome of a decision point in the code. Think of the true and false paths coming out of an IF statement, or each case in a Swiss CH statement. Coverage is measured as the percentage of these decision outcomes or branches that have been exercised.
So branch coverage is better.
Usually, yes. Achieving 100% branch coverage often implies you've achieved 100% statement coverage, because you have to execute the statement within the branch. But the reverse isn't true. You could execute every statement without necessarily taking every possible branch through the code.
What's the main takeaway about the value of white box techniques then? Why bother if you have good black box tests?
Well, black box testing alone doesn't tell you how much of the underlying code was actually exercised by your tests. You might have great requirements coverage but miss entire sections of the code. White box techniques give you an objective measure of code coverage.
What does that help with?
It shows you which parts of the code haven't been tested, providing clear information to help you design additional test cases to increase coverage in those areas. Ultimately, achieving a target level of code coverage increases confidence in the software's reliability and thoroughness of testing.
Okay, that makes sense. Moving to the third category, experience-based techniques. These sound less formal, maybe more reliant on the tester's gut feeling.
They do rely heavily on the tester's skills, intuition, background knowledge, and past experience, absolutely. And they are incredibly valuable, often finding defects that might be missed by the more formal, systematic black box or white box techniques. They complement the other approaches. The syllabus usually covers error guessing, exploratory testing, and checklist-based testing.
Error guessing sounds like fun.
It can be. It's literally about using your experience and knowledge to anticipate or guess where errors, defects, or failures might occur. This could be based on knowing common software flaws, understanding typical mistakes developers make in certain situations, knowledge of the application domain, or just anticipating problematic areas in the software.
Do you just guess randomly?
Not entirely randomly. You might use systematic approaches like fault attacks, which involve using predefined lists of common errors or potential vulnerabilities derived from past projects, bug databases, or security knowledge, and trying them out on the current system.
Okay. Exploratory testing.
Wow.
This one sounds adventurous, like charting unknown territory.
It kind of is. Exploratory testing is defined as simultaneous test design, execution, and evaluation while you're actively learning about the test object. You interact with the software, explore its features, take notes on what you observe, and design and run new tests on the fly based on what you discover and your hypotheses about potential problems.
Is it structured at all?
It can be. A more structured approach is session-based test management, SBTM. This involves using time-boxed test sessions, for example, 90 minutes, clear test charters or missions for each session, what you're trying to explore or test, and debriefings afterwards to discuss findings and record results, often using test session sheets.
When is exploratory testing most useful?
It's particularly valuable when specifications are poor or missing, when there's significant time pressure, or simply as a powerful way to complement more formal testing techniques by finding issues those scripted tests might miss. Its effectiveness, though, is highly dependent on the individual tester's skills, their analytical ability, curiosity, creativity, and domain knowledge.
Can you use other techniques within exploratory testing?
Absolutely. A skilled exploratory tester might mentally apply principles of boundary analysis or equivalence partitioning while exploring, or use error guessing based on what they're seeing.
Okay. And the last experience-based one, checklist-based testing.
This is quite straightforward. It involves using predefined lists of checks, actions, conditions, or items to be verified during testing. These checklists are typically created based on experience, perhaps derived from common errors found in the past, like error guessing lists, knowledge of specific failure types, or relevant standards.
What's the key to using checklists effectively?
Checklists provide consistency and guidance, ensuring certain areas or checks aren't forgotten. However, they should be kept reasonably high level to allow for tester variability and insight. Crucially, checklists should be reviewed and updated regularly based on defect analysis from current and past projects, and kept concise and relevant to be truly useful.
Got it. The syllabus also mentions collaboration-based test approaches, which seems to link back to those team dynamics we discussed earlier.
Right. These techniques really emphasize preventing defects through better communication and collaboration, especially common in agile teams where that cross-functional interaction is key. Collaborative user story writing is a prime example highlighted.
User stories, they have the 3 C's, right? Card, conversation, and confirmation.
Exactly. The card is the brief description. The conversation is the crucial part where the whole team, business representatives, developers, testers, discusses the story to build a shared understanding from all perspectives. And the confirmation part is represented by the acceptance criteria, which define how we'll know the story is done correctly.
So collaboration is key to getting good stories.
Absolutely. That collaborative conversation ensures everyone has a shared vision, potential ambiguities are resolved early, and the acceptance criteria are clear, testable, and truly reflect the desired behavior and value. Good user stories ideally follow the INVEST principles. They should be independent, negotiable, valuable, estimable, small, appropriately sized, and testable.
And acceptance criteria, you said, are essentially the test conditions for the story.
Yes, pretty much. They are the specific conditions that the implementation of the user story must meet to be considered complete and accepted by the stakeholders. They result directly from that conversation part.
What are they used for?
They're used to define the scope of the story more clearly, help the team reach consensus on what done means for that piece of work, describe specific scenarios, both positive happy path and negative or edge cases, form the primary basis for acceptance testing activities, and they're also vital for planning and estimation. Several formats exist for writing them.
Okay. How does acceptance test-driven development, ATDD, build on this idea of collaborative stories and acceptance criteria?
ATDD takes those collaboratively defined acceptance criteria and uses them to derive concrete test cases as part of the system design process, ideally before the corresponding code is written. It formalizes the confirmation aspect.
How does that work in practice?
It often starts with a specification workshop where the team, business, dev, test, analyzes the user story and its acceptance criteria together. They then collaboratively create specific test cases, often framed as examples of behavior, based directly on those criteria.
What kind of test cases?
These test cases act as concrete, executable examples of how the software should behave. They can cover functional or non-functional aspects, positive and negative scenarios. They are typically expressed in a way that's understandable to both technical and non-technical team members. Very often, these ATDD test cases are then automated, effectively becoming executable requirements or specifications that provide living documentation and a robust regression safety net.
So ATDD is like using tests to solidify the requirements and actually guide the development process itself. That wraps up the techniques really nicely. Let's move into the management side of testing now. Test planning seems like the logical place to start.
Definitely. Test planning is fundamental. It's all about defining your testing objectives and figuring out the best approach to meet them within the inevitable project constraints, time, budget, resources, risks.
Why is a formal plan so vital?
Well, it serves several purposes. It documents the means and schedule for achieving the test objectives. It ensures the test activities align with the overall project goals and exit criteria. It acts as a key communication tool for all stakeholders. It forces you to adhere to any organizational test policy or strategy, or explicitly explain deviations. But maybe most importantly, it guides the tester's thinking and forces the team to confront potential challenges upfront, like identifying risks, figuring out resource needs, estimating effort and cost, and planning the schedule.
What kind of things does a test plan typically include? What's in there?
It usually covers quite a bit. Things like the testing context, the scope, what's in, what's out, the objectives, the test basis, the documents or requirements you're testing against, any assumptions being made and constraints you're working under, who the key stakeholders are and how communication will be managed, a risk register identifying potential product and project risks related to testing.
And the approach.
Yes, the detailed test approach is core. This covers which test levels and types you'll perform, the techniques you plan to use, the deliverables you'll produce, the entry and exit criteria for various activities, the level of test independence required, the metrics you'll track, plans for test data and the test environment, and any planned deviations from the standard test strategy. And of course, you need budget and schedule information.
How do testers specifically contribute to planning, especially in those faster-paced, iterative, or agile environments? It feels like planning might be different there.
It is more continuous, but testers play a crucial role. In release planning, which looks ahead across multiple iterations, testers participate actively. They help refine user stories to make them testable. They contribute to defining clear acceptance criteria. They participate in risk analysis for the features planned in the release. They help estimate the overall test effort, determine the appropriate test approach, and plan high-level release testing activities like end-to-end or performance tests.
And within each iteration.
In iteration planning, which focuses just on the upcoming short cycle, testers get more granular. They perform detailed risk analysis for the specific stories being pulled into the iteration. They assess the testability of those stories. They help break stories down into smaller testing tasks. They estimate the effort required for those specific tasks, and they identify both functional and non-functional aspects that need to be tested within that iteration.
You mentioned entry and exit criteria as part of the plan. Can you clarify the difference again and why they're important?
Sure. Entry criteria are the set of preconditions that must be met before you can effectively start a specific test activity, like system testing or performance testing. If you try to start without meeting them, maybe the test environment isn't fully configured or the software build fails basic smoke tests, the activity will likely be much more difficult, costly, and risky. You might waste a lot of time.
Okay, so they're readiness checks. What about exit criteria?
Exit criteria define what must be achieved to consider that activity complete. They signal when you can stop testing at that level or for that iteration. They should be defined for each test level and will differ based on the specific test objectives.
What are some examples of typical criteria?
For entry criteria, you might need things like resource availability, people, tools, testware availability, approved test basis documents, written test cases, the test environment being ready and verified, and maybe the successful completion of earlier test levels or basic build stability checks, smoke tests.
And for exit criteria?
Exit criteria often involve reaching certain thoroughness measures, like achieving a target percentage of planned test case execution or requirements coverage. They might relate to defect metrics, like the number or density of unresolved defects falling below a defined threshold, especially high-severity ones. Or maybe binary criteria, like all planned tests have been executed, all static testing is complete, all found defects are reported, or a certain suite of regression tests is automated and passing.
What if you just run out of time or budget?
That's a reality. Running out of time or budget can sometimes be considered a valid exit criterion, but only if the stakeholders are made explicitly aware of the associated risks of stopping testing early and they formally accept those risks. In agile contexts, exit criteria often align closely with the team's definition of done, and entry criteria might map to a definition of ready for starting work on a story.
Estimating the effort required for testing that can be notoriously difficult. What techniques does the syllabus suggest to help with that?
Yeah, Estimation is definitely challenging. It's always an approximation based on assumptions and available data, so it's subject to error. One key principle is that breaking down large testing tasks into smaller, more manageable ones usually leads to more accurate estimates overall.
What are some specific techniques?
The syllabus mentions a few common ones. There are ratios-based techniques where you use historical data from similar past projects, like the ratio of testing effort to development effort, or defects found per KLOC to estimate the current project. Extrapolation involves measuring progress and effort spent early in the current project and then projecting or extrapolating that to estimate the remaining effort.
What about using expert judgment?
Yes, there's three-point estimation where you get optimistic, most likely, and pessimistic estimates for a task, and you use a formula, like Piret, to calculate a weighted average or determine a range. And wideband Delphi is a more formal expert consensus technique involving multiple rounds of anonymous estimation and discussion among experts to converge on a more reliable estimate.
Okay. Once you have your test cases designed and ready, how do you decide which ones to run first, especially if you have limited time?
That's test case prioritization, and it's crucial for maximizing the value of your testing time. There are several common strategies. Risk-based prioritization is very common. You execute the test cases that cover the highest product risks first to find the potentially most damaging defects early.
What else?
There's coverage-based prioritization, where you might prioritize tests that give you the broadest coverage of requirements or code structures quickly, or tests that specifically target areas not yet covered. Requirements-based prioritization involves ordering tests based on the priority assigned to the underlying requirements by stakeholders. And of course, practical things like dependencies between test cases and the availability of specific resources or environment configurations also affect the execution order.
The syllabus briefly mentions conceptual models like the test pyramid and testing quadrants. What are those about? Are they techniques?
Not techniques themselves, but more like conceptual models or heuristics to help teams think about and discuss their testing strategy, especially in agile contexts. The test pyramid, popularized by Mike Cohn, is a visual metaphor suggesting you should have a large base of fast, cheap, automated unit tests, a smaller middle layer of automated integration or service-level tests, and a very small top layer of slower, more expensive end-to-end UI tests, often manual. It promotes pushing tests down to the lowest effective level.
And the testing quadrants.
Brian Merrick's testing quadrants model is another way to categorize different types of testing often found in agile projects. It uses two axes: business-facing versus technology-facing tests, and tests that support the team versus tests that critique the product. It helps teams ensure they have a balanced testing approach covering all four quadrants, things like unit tests, functional tests, exploratory tests, performance tests, etc., and facilitates discussions about who perform which types of testing.
So models to help frame the conversation and strategy useful. Okay, risk management is clearly deeply integrated into planning and managing testing. How does the syllabus formally define risk?
Risk is defined as a potential event or condition that, if it occurs, could have an adverse or negative outcome. It's typically characterized by two main factors: the likelihood or probability of the event happening, and the impact or consequence if it does happen.
And combining those gives you...
Combining likelihood and impact gives you the risk level, basically, a measure of how serious the risk is. The higher the risk level, the more important it is to pay attention to it and potentially do something about it.
And the syllabus distinguishes between two main types of risk relevant to testing.
Yes, it draws a clear distinction between project risks and product risks. Project risks are those potential problems that threaten the success of the project itself. Things related to management, control, resources, schedule, budget, scope, organizational factors, people issues, technical challenges, or problems with suppliers. They impact the project constraints.
And product risk.
Product risks, on the other hand, are related to potential quality problems in the software product itself. These are the risks that testing is primarily focused on identifying and mitigating. They represent the possibility that the software might fail to meet the legitimate needs and expectations of its users or stakeholders.
What are some concrete examples of product risks?
Oh, things like the risk of missing or incorrect functionality compared to requirements, the risk of poor performance under expected load, the risk of security vulnerabilities being exploitable, the risk of poor usability leading to user frustration or errors, the risk of data corruption or loss. the risk of the system not being compatible with the required operating environments. If these risks materialize as actual failures, they can lead to consequences like user dissatisfaction, financial loss, damage to reputation, legal penalties, or even physical harm in safety-critical domains.
So performing product risk analysis is absolutely key to guiding the testing effort effectively.
Absolutely. The main goal of product risk analysis in testing is to identify potential quality issues early and use that information to focus the test effort where it's needed most, thereby minimizing the residual risk, the risk that remains after mitigation efforts like testing have been performed.
What does the analysis process involve?
It typically involves two main steps. Risk identification, which is about generating a list of potential product risks through techniques like brainstorming, workshops, checklists, analyzing requirements, or looking at historical data. And then risk assessment, which involves analyzing each identified risk to determine its likelihood and impact, calculating its overall risk level, and then prioritizing the risks based on their level.
How do you determine the level? Quantitatively.
It can be quantitative, maybe multiplying numerical scores for likelihood and impact, or it can be qualitative, using categories like high, medium, low, often visualized using a risk matrix. The key is to prioritize consistently.
And how does the outcome of this risk analysis specifically influence the testing activities?
It's a direct and crucial input to your test strategy, planning, design, and execution. The prioritized risk list helps determine the scope of testing, which features or areas need more focus, the appropriate test levels and types to apply, the selection of 10 techniques and the required coverage levels, more rigor for high-risk areas, the estimation of effort needed, the prioritization of test case execution, test highest risks first. And it can also highlight where non-testing activities, like additional reviews, specific training, or architectural changes, might be needed to mitigate certain risks.
Okay, so once the risks are analyzed and prioritized, you need to actually do something about them.
Yeah.
How does the syllabus describe risk control?
Risk control encompasses the actions you take in response to the analyzed risks. This includes risk mitigation, implementing specific actions designed to reduce the likelihood or impact of a risk, thus lowering its overall level. And risk monitoring, continuously keeping an eye on the identified risks, checking if the mitigation actions are actually effective, gathering more information about the risk, and identifying any new or emerging risks during the project.
What are the typical response options for a risk?
Common options include mitigation, taking action to reduce it; acceptance, deciding the risk level is low enough to live with; transfer, shifting the risk to another party like buying insurance or outsourcing; or developing a contingency plan, having a backup plan ready just in case the risk materializes.
And how do you mitigate product risks, specifically through the act of testing? What testing actions help?
You use various testing activities strategically as risk mitigation actions. This could mean assigning more experienced testers or ensuring appropriate independence for testing high-risk features, conducting targeted static analysis or rigorous reviews on critical work products like requirements or security designs, applying specific, powerful test techniques like boundary value analysis, decision tables, or state transition testing where they are most likely to find critical defects related to the risk. Choosing appropriate test types like performance, security, or usability testing focused on risk areas. And ensuring thorough dynamic testing and robust regression testing, particularly in those high-risk parts of the system.
It's really clear that risk management isn't some separate activity. It's deeply woven into the fabric of effective test management and execution. Okay, finally, let's cover the topics of test monitoring, control, and completion. What's the essential difference between monitoring and control?
Think of it this way. Test monitoring is the ongoing process of gathering data and checking progress. You're collecting information about your testing activities. Are you on schedule? Within budget? You're also evaluating the quality of the test object itself, how many defects are being found, what's their severity, and you're tracking the effectiveness of your testing. Are you meeting your coverage targets? Are the exit criteria being met?
So monitoring is about observation and data gathering. What's control then?
Test control is about using the information gathered during monitoring to make decisions and take corrective actions when things deviate from the plan or when risks change. These actions are sometimes called control directives.
Can you give examples?
Sure. If monitoring shows that test execution is falling significantly behind schedule, a control action might be to reprioritize the remaining tests to focus on the highest risk areas first. If monitoring reveals an unexpectedly high number of defects in a particular component, control might involve allocating more test resources to that area, reevaluating the entry criteria for the next test level, or even adjusting the overall project schedule. It's about actively steering the testing effort based on real-time feedback.
So monitoring gathers the data, and control acts on it to stay on course.
Got it. And test completion, when does that happen?
Test completion activities happen when a defined test effort finishes. This could be at the end of a specific test level, like system testing, the end of an iteration in an agile project, upon achieving a major project milestone like a release, or even when a maintenance release is done.
What's involved in completion? It involves collecting and finalizing all the data from the completed activities, archiving the testware, plans, cases, results, logs, consolidating lessons learned, which is crucial input for retrospectives and future projects, and usually creating a final test summary or completion report. It's about wrapping things up formally.
What kind of metrics are typically monitored throughout this process to get that information for monitoring and control?
There's a wide range depending on the project's goals. You monitor project progress metrics like tasks completed versus planned, effort spent, test progress metrics, test cases planned, written, executed, passed, failed, test environment preparation status, product quality metrics, defect density, defect find fix rates, trends in defect severity or status, maybe metrics related to reliability or availability, risk metrics, tracking the number or level of outstanding product risks, coverage metrics, requirements coverage, code coverage, risk coverage, and sometimes cost metrics related to testing activities.
And how do you communicate all this information effectively? Who needs to know?
That's where test reporting comes in. You typically create test progress reports periodically during the testing activity. Their main purpose is to provide status updates to stakeholders and support ongoing test control, allowing for informed decisions and plan adjustments. Then you create test completion reports or test summary reports at the end of the activity. These summarize the entire effort, provide an overall assessment of quality, document results against exit criteria, and inform decisions about subsequent testing or release readiness.
What's the main purpose of these reports?
Primarily, they support decision-making. They provide stakeholders with the information they need about quality, progress, and risks. They help measure progress against the original objectives and criteria, and they clearly communicate the status of the testing effort. It's vital to tailor the content, level of detail, and communication method. Maybe it's a formal document, maybe it's a dashboard, maybe it's an email summary, maybe it's a verbal update to the specific audience, whether they are project managers, developers, business users, or executives.
Tailoring the message. Always good advice for any communication. The syllabus also briefly touches on configuration management and defect management, again in this management section, just to reinforce their importance.
Yes, it reiterates that configuration management, same as we discussed earlier, is crucial foundational support for reliable testing. It's needed to identify, track, version, and control all the configuration items, including test items and testware. It maintains traceability and ensures you can reproduce test results accurately. In modern DevOps pipelines, automated CM is absolutely key.
And defect management.
Defect management is the structured process for handling anomalies or potential defects from the moment they're discovered until they're resolved or closed. It involves a defined workflow, logging the issue, analyzing it, classifying its severity and priority, deciding on the response, fixed, defer, won't fix, etc., getting it fixed if applicable, confirming the fix, and finally closing the defect report.
Does this apply to static testing finds too?
Yes, the principles apply equally to anomalies found during static testing, like reviews, and failures observed during dynamic testing. The objectives are to provide clear information to enable resolution, track the status of issues, monitor the overall quality of the product, and gather data that can be used for process improvement, identifying patterns or root causes. The syllabus often lists the typical content expected in a good defect report, things like a unique identifier, clear title, date, author, details about the test object and environment, steps to reproduce, expected versus actual results, assigned severity and priority, current status, and any relevant references or attachments. Clarity and detail here are essential for efficient fixing.
That structured process for handling defects really is key to closing the loop on findings and learning from them. Okay, finally, the syllabus looks at test tools. We've mentioned automation a few times, but how do tools fit into the overall testing picture?
Tools can support and facilitate many, if not most, of the testing activities we've discussed, aiming to improve efficiency, effectiveness, consistency, and repeatability. There's a huge range of tools available.
Like what?
Examples include tools for test management, handling requirements, test cases, execution scheduling, reporting, defect tracking. Tools for static testing, Static code analyzers that find potential bugs or standards violations without running the code. Tools to support test design and implementation, generating test data, creating test case skeletons. Tools for test execution and coverage measurement, automating test script execution, measuring code coverage. Specific tools for non-functional testing, load performance testing tools, security vulnerability scanners, tools integral to DevOps pipelines, CI/CD servers, build tools, deployment tools, collaboration tools, wikis, chat platforms, and even basic but powerful tools like spreadsheets are often used for test planning, tracking, or data management.
And for many people, when they think test tools, they immediately think test automation. What are the big potential benefits and, importantly, the risks of test automation, according to the syllabus?
Okay, the potential benefits are significant, which is why it's so popular. Automation can save a lot of time and effort on repetitive manual tasks, especially regression testing. It ensures consistency and repeatability, preventing human errors in execution. It can provide more objective assessment, for instance, through automated coverage measurement. It often makes accessing test results and metrics easier through automated reporting and dashboards. Crucially, it can drastically reduce test execution times, allowing for earlier defect detection and faster feedback loops, especially in CI/CD. And ideally, it frees up human testers to focus on more challenging and valuable activities like designing new tests, exploratory testing, or usability analysis.
Sounds amazing. Almost too good to be true. What's the catch? What are the risks?
The risks are also significant and unfortunately often underestimated. One of the biggest is having unrealistic expectations about what automation can achieve, how quickly, and how easily. Another is making inaccurate estimates of the considerable time, cost, and effort required not just to purchase a tool, but to implement, integrate, and crucially maintain the automation framework and test scripts over time. Automation isn't a one-off cost.
Well,
Insufficient budget, time, or skills within the team to develop and maintain robust automation is a common failure point. There's also the risk of becoming overly reliant on a specific tool or vendor lock-in. Integration challenges with the application under test or other tools in the environment can be complex. And perhaps the most subtle but dangerous risk is over-reliance on automation leading to a false sense of security, potentially missing important defects that different approaches, like manual exploratory testing, might have found. The syllabus really emphasizes that successfully introducing and leveraging a test tool requires substantial effort that goes far beyond the initial purchase price.
that point about needing significant effort beyond the purchase for implementation and maintenance is absolutely crucial. Automation is a serious software development project in itself, isn't it?
Absolutely. It needs to be treated as such. It's a powerful tool to support good testing practices, but it's not a magic bullet, nor is it a replacement for sound testing principles or skilled testers.
So we've taken a pretty serious deep dive into the foundational concepts laid out in the ISTQB syllabus. It's clearly so much more nuanced and involved than just, running some software and looking for bugs.
Indeed. It's about understanding the why behind testing the core principles. It's about the how the lifecycle activities, the different levels and types, the specific techniques for analysis and design. It's about managing the process effectively, dealing with risk proactively, and leveraging tools appropriately. It really provides that essential common language and framework for the profession.
And thinking about your own experience, maybe listening to this, you can recall situations, maybe the impact of skipping static analysis early on, or not having clear exit criteria for a phase, or perhaps you've encountered a bug that, in hindsight, something like boundary value analysis or state transition testing could have easily found if applied systematically.
Right.
How might implementing just one practice discussed today, maybe better defect reporting, focusing on impact, or fostering closer collaboration around acceptance criteria, change the dynamics and outcomes on your own team?
Exactly. These aren't just abstract concepts listed in a syllabus. They are practical tools, techniques, and perspectives that, when understood and applied thoughtfully in your context, can genuinely increase the effectiveness and efficiency of your testing efforts. Ultimately, that leads to delivering better quality software and fostering a stronger culture of quality within your team and your organization. Understanding this foundation is really step one on what should be a continuous journey of learning and improvement in testing.